Hello, hello, hello. Est-ce que tu m'entends?
Ah, oui, là c'est mieux, là je pense. Il doit nous entendre.
Ouais, là j'entends. J'entends, j'entends.
Ok. Ouais, je vous entends.
Ouais, j'entends. Vous m'entendez aussi?
Ouais, ouais, super.
Ok, good. Je t'entends pas très fort, hein. Alors, parle un peu, Paul.
Tu vas bien?
Ouais, ça va, mais c'est pas, c'est vrai que le son est pas hyper fort.
Oui, le son est pas fort. Ok.
Ouais.
Il est quelle heure à Montréal? Il est 8h, 9h?
Ouais, 8h moins 5. C'est ça.
C'est plus. Ouais, alors, bon. Ouais, ouais. Ouais. Et, faut que tu prends 2 minutes. Ça là. Ouais. Ok. Ok.
J'ai essayé de changer mon micro. Vas-y, redis-moi deux, trois mots, Paul, là, que je vois si c'est plus mieux le son.
Il est quelle heure à Montréal?
Et- Ouais, ouais, c'est mieux là, d'accord, c'est peut-être le micro. Ok, ok. Non, non, c'est bien.
Mais collé, normalement, je crois
On est
qu'on est
collé?
collé à soi, non? On n'est pas
Ah
tout
bah,
près.
je suis désolé pour.
Parce pas de, j'essaie de pas postillonner, hein.
Ah, ouais, quand même.
Fantastique. Vous connectez, les gars? Nico? Yo, Nico?
Ouais, mon son est coupé. Salut, salut.
Bon, je vois personne.
Il y a une peur?
Ah oui, voilà. Toi, tu vois pas.
Non.
Ouais, salut Nico, ça va?
Salut
Tu nous
Mathieu, ouais,
vois?
ouais, ça va bien.
Qu'est-ce que t'as comme image, toi? Tu vois quoi avec la chouette? Tu vois
Ouais,
toute la salle?
j'ai deux images, là, je vous vois tous les deux, donc je vois une image Paul et une image panoramique de la salle derrière. Une image,
Super,
voilà. Ouais.
bien
Image
fait.
grand angle. Ouais.
C'est bien fait. Bon, bien sûr. Donc, bon, on s'est mis d'accord. Hello Stéphane, pour le jury, Nico, c'est toi qui désigne.
Ah non, moi, on s'est pas mis d'accord. Donc, le président, tu veux dire?
Oui, il faut qu'on choisisse un président.
Tout à fait, tout à fait. Non, non, on n'a pas désigné de président, hein, comme j'étais pas là. Donc voilà, naturellement, nos regards se tournent vers toi. Mais
Ouais. Et merci, merci, cher confrère.
merci.
Salut Frédéric. Hello.
Bonjour tout le monde.
Bonjour.
Bonjour.
Hello Alex.
Salut
Bonjour.
Alex.
Stéphane. Salut
Je peux
Stéphane.
remettre tout le monde là, 2 secondes, le temps que je fasse le- on est complet du coup. Ouais,
Bon,
c'est parti.
ouais. Donc,
Ok.
on parlait de la désignation du président. Il semble naturel que ce soit Mathieu qui joue ce rôle si ça convient à tout le monde.
Ouais, parfait.
Parfait. Bon, super.
Super. Stéphane?
Stéphane, t'es d'accord?
Stéphane, can you hear us?
Can you-
Stéphane, we can hear you. Yes,
Ah, nous, on t'entend pas, Stéphane. We cannot hear you.
yeah.
Hmm.
On va attendre que Stéphane Stéphane, tu nous dis, hein, essaye de faire quelque chose, nous on t'entend pas,
Ouais.
on ne voit pas, on t'entend pas, on ne sait pas si tu nous entends.
Je pense qu'il avait écrit dans le chat qui nous entend.
Il a écrit dans le chat, il a écrit dans le chat qu'il nous entend, c'est ça?
Il nous entend.
Ok.
Et nous, on l'entend.
C'est une première étape. Ok. Et demande-lui s'il pense qu'il pourra en parler plus tard. C'est vrai que pour le moment, on n'a pas de temps.
Est-ce qu'il voit les slides? Du coup, les slides, et puis on peut commencer, il va répondre sur sa tablette.
Ok. Very good, very good.
Ok.
Ok, bon, alors on peut commencer. Donc, mes collègues, je vais commencer en français avant de passer en anglais. Mon désigné président de jury, ou Paul, vous allez nous présenter vos travaux pendant environ 45 minutes et puis après on va passer à la séance des questions. Je vais juste présenter avant un petit peu le jury. Donc il y a un certain nombre de personnes qui sont en... Stéphane, je pense que je vais commencer à connaître un peu le bordel dans le son. Voilà, donc pour le moment il y a un écho, mais bon, je continue. Donc à distance, on a le professeur Alex Alaï de l'EPFL. Voilà, on te voit, Alex, vous avez dit bonjour tout à l'heure, donc professeur à l'EPFL. Euh, on a aussi Frédéric Jury, tu nous entends aussi, Frédéric, hein, qui
Oui,
c'est aussi
bonjour. Je vous entends très bien. Bonjour tout le monde.
professeur à l'Université de Caen. Euh, on a aussi donc Stéphane Latuyère, qui est maintenant DR, donc directeur de recherche à l'IRIA à Grenoble. Voilà. Et puis donc Nicolas Tom, donc directeur de cette thèse, qui est au Canada en ce moment, à, à Montréal. Je ne sais pas où tu es, dans quel truc. Bon, CNRS, disons, t'es dans un labo CNRS. Voilà. Et puis, donc, autour de moi, il y a Vicky, donc toujours Calo-Gayton, pas mal, voilà, ok, qui est donc professeur à l'école polytechnique, d'une part, donc, pardon, j'ai oublié de dire, donc Stéphane et Frédéric étaient les deux rapporteurs, et Vicky examinatrice, comme Alexandre. Et on a aussi donc Jean-Emmanuel Aujard à ma droite, qui est donc ton encadrant côté Thalès. C'était une case cible. Voilà. So I'm going to switch to English now. So you have something like 45 minutes around all to present your PhD entitled Structured Visual Representation with Foundation Models. And after we will have this Q&A session, starting with the first the reviewers, and then after the rest of the jury. Okay, please, the floor is yours.
So thank you very much, everyone, for being here today. I'm very pleased to present the work that I've been doing during my PhD. So this talk is about structured visual representations with foundation models. The first question that arises when reading this title is, what is a foundation model and what are structured visual representations? So to develop truly capable AI systems, we need some models that can capture and understand the world, capturing its structure, relationships, and patterns. And today we have access to a tremendous amount of data from the internet, some images, text, videos, and more. And this offers a broad and diverse picture of the world. And the key idea is to leverage this vast uncurated data by training some models that can first learn directly from it without labels, and second, align the different modalities connecting vision to language and other signals so that the models develop a structured internal representation of the world. And what truly enables foundation models is scale. We train a very large model on enormous amounts of data for long periods of time. And this scaling in model size, data, and compute allows them to capture rich and general purpose representations that can be adapted to many different tasks. And this approach deviates from the standard approach in machine learning, where a model is trained for each individual task. Here, instead, we train a shell model that can be adapted to a variety of downstream applications. And in this presentation, we are particularly interested in foundation models for visual data that are often called foundation vision encoders. And the goal of training such models is to learn compact representations of images that capture their semantic meaning as effectively as possible. And we expect these compact representations to be structured, that is, to exhibit certain desirable properties that make them easily transferable to downstream applications. And among the desirable properties of foundation vision encoders, we can highlight first the semantic disentanglement. We expect visual representations to be high-level, embedding the semantic content of a scene into distinct components of the feature space, rather than focusing on low-level cues such as textures or colors. And this disentanglement allows the model to reason and recognize about what is present in the scene, rather than just memorizing appearance. Then representation should be especially coherent, preserving the geometry, layouts, and relationships between the regions and an image. And this property is essential for dense vision tasks, such as segmentations, keypoint matching, or desestimation. And finally, representations should be transferable easily, meaning that they can be efficiently reused across tasks and modalities, from classification, segmentation, or text-to-image alignment. And over the past few years, several pre-training paradigms have been proposed to build foundation vision encoders, each offering its own strengths and limitations depending on the learning objective and the data setup. So let's have a closer look at some of the existing pre-training paradigms. The first one is contrastive learning, and a well-known example of contrastive learning is the model CLIP. So in CLIP, we work with image text pairs. Each image is associated with its corresponding caption. And the idea is to train the model so that image and text representations of a matching pair are close together in a shared multimodal embedding space. And at the same time, the model learns to push apart representations of mismatched pairs, ensuring that each image aligns only with its correct description. Another powerful training paradigm is self-distillation. In self-distillation, there are no paired data or labels. Instead, we have two networks, a teacher and a student, that view different augmentations of the same image. So the student learns to match the teacher's output representations so that both networks produce consistent embeddings of the same visual content. And typically, the teacher is a delayed, smoothed out version of the student, which stabilizes training and prevents collapse. And although at the start of the training, both models are identical, the only way for the system to converge is for the model to develop a meaningful internal structure that is to organize the visual representations in a way that captures the underlying semantics of the images. And through this process, the model learns rich and semantic representations that without any supervision. And a third major pre-training paradigm is mask image modeling that we'll illustrate here with the mask autoencoder approach. The idea is quite simple. We mask a large portion of the patches of an image, and we train the model to reconstruct the missing parts from the visible ones. So by learning to predict the missing visual information, the model is forced to understand the global structure of and semantics of images and not just local details. And through this self-supervised process, the MA learns visual representation that transfer well to downstream tasks, even though it never sees a single label. And whereas weakly supervised and self-supervised paradigms focus on representation learning, generative modeling instead aims to capture and reproduce the data distribution itself. So generative modeling is about sampling data from the underlying distribution of real images, essentially the distribution that the universe uses to produce the data that we observe. And of course, we don't know this true distribution because it depends on extremely complex factors such as physics, history, social constraints, and more. And our goal is to learn a model that approximates this data distribution so that we can generate new samples that resemble the real images that we observe. And the typical approach is to start from a random Gaussian noise and pass it to a generative model. And the model is trained so that the distribution of generated sample matches the real distribution as closely as possible. And recently, different models have become the state of the art in image generation. The core idea is to gradually add noise to data until it becomes pure noise, and then to learn to reverse this process step by step to map random noise back into a realistic image. And during this training, the model learns how to denoise images at various noise levels, capturing effectively the structure and semantics of natural images. And at generation time, we start from Gaussian noise and iteratively denoise it to sample from the learned data distribution. And these diffusion models can be conditioned on text descriptions to perform text-to-image generation. And this conditioning is achieved through cross-attention mechanisms that allows the model to align visual features with a textual concept. So in practice, we have a pre-trained text encoder, such as Clip, that converts the input prompts into a sequence of text embeddings. And we make these text embeddings interact with the visual content with the cross-attention layers in the diffusion model. So at each step, these layers let image features attend to the text embeddings, guiding how noise is transformed into a meaningful visual content that aligns with the textual prompt. So through these cross-attentions, the model learns to associate words with visual attributes, and this allows to generate images that reflect the semantics of the text prompt. And beyond text prompt, different models can be guided by other conditional signals, such as depth maps, segmentation maps, poses, or more, in order to control the structure and layout of generated images. And one simple way to condition a pre-trained model is to train some lightweight adapter networks that process the conditioning input and produces feature maps that are compatible with the different model's internal representations. And these adapter features are injected into the different model at various layers, conditioning the denoising process while keeping the original different weights frozen. So this design allows different models to adapt to new tasks and new inputs efficiently, all while preserving the rich generative power of pre-trained models. So overall, different base generative models excel at producing high-quality image from diverse conditioning inputs. They can be trained at scale and naturally align with text. So this makes them strong candidates for unifying vision and language within a single framework. And these properties indicate that different models may internally encode rich, semantically structured representations with a potential far beyond image synthesis. However, their capacity for structured visual understanding remains largely unexplored. And this raises the following question: how can different foundation models be leveraged for structured visual understanding? And throughout this PhD, I have focused on understanding and analyzing this new class of models from three complementary perspectives. The first axis explores diffusion models for what they are designed to do, that is, as generative models. But in this part, we investigate how pre-trained text-to-image diffusion models can be repurposed for zero-shot video editing, addressing the challenges of temporal consistency and coherence. So this work is presented in the first chapter downstream computer vision tasks, such as a zero-shot image segmentation. So these questions are the focus of the second chapter, difficult. And finally, the third axis addresses a more general limitation shared across foundation vision encoders, which is the spatial resolution of the dense visual representations. And in the final chapter so far, we propose an efficient upsampling module that allows semantic. This image of a tiger, and we want to edit it as an image of a lion. There are three core requirements we want to meet in order to be satisfied with our edits. The first one is the edit consistency. We want the semantics of the edited image to match the semantics of the input text query. So if we obtain this image of a cat, for example, we're not satisfied with the edit. The second one is the minimal edit requirements. We do not want to edit the whole image content, but only the semantic region that is associated to the semantics of the input text query. And finally, we want our edit to be realistic or at least satisfying from a human perspective. And this task is extremely challenging because first we lack some supervised data. That is, we lack some large-scale data sets of real images that are associated to their edited counterparts. And second, we need to come up with some quantitative metrics in order to evaluate the quality of the edits performed. And these metrics are super important because there exists a trade-off between these objectives. We need to modify the semantics of an image while preserving the original content as much as possible. And when it comes to video editing, the temporal consistency challenge adds up to these requirements. And some early methods propose to directly inject the temporal dynamics into pre-trained text-to-image diffusion models with some dedicated spatial temporal. Are you good online? There has been the disconnection on my side.
Yeah. There have been disconnections, so the sound were a bit off for 1 minute, let's say.
Okay.
Now we hear you well now.
Okay, great.
And the slides are not shared anymore.
Oh, okay.
That's fine now. Yeah.
Right. So the idea is to collapse the temporal dimension in order to represent some video content on a 2D space. So let's say that we have this video of a motorbike driving down a road. We want to decompose it into a set of layers called atlases. So here, for example, we have two atlases, one foreground, which is the motorbike, and one background, which is the rest of the scene. And this foreground background decomposition is defined by the user, and it enables handling the occlusions when reconstructing the video frames. Because the ultimate goal with these 2D atlases is to make it possible to query these 2D representations in order to reconstruct the original video frames. And if these 2D representations are both interpretable and semantically meaningful, a user could manually edit them and then query the modified representations to produce an edited video content in a temporally consistent manner. So I will not go into the details of how we obtain these 2D representations, but from now on, we can assume that we know how to get them. And as I said, this decomposition allows to manually edit videos as long as the atlas representations are semantically meaningful. And Text2Live extends this idea by automating video editing through text guidance, optimizing a generator network directly in the 2D atlas space. So the input video is decomposed into 2D atlas representations, and we train a generator to produce an edit layer that is composited over the chosen atlas representation. And the edited atlas is then queried to create some frame edit layers that are composited over the original frames. So this generator is optimized by is trained by optimizing first a reconstruction loss to preserve the original video structure and consistency, and second, a semantic loss based on the clip embeddings to ensure that the edits align with the semantic of the input text prompt. So this approach allows automatic text-driven video editing that maintains temporal consistency and semantic fidelity across frames. However, as the generator requires to be optimized for each target edit, which takes roughly 40 minutes, this is quite computationally expensive when we want to perform multiple edits. Unfortunately, we now have powerful pre-trained text-to-image generators with different models. So the question is now, how can we combine the strengths of layered atlases with the generative power of text-to-image diffusion models? So the framework video edit that I propose is quite simple. So we have an input video, here a bus driving down a road, and we decompose it into a set of 2D atlases. And now say that we want to edit the bus. So we take the atlas corresponding to the bus, and we are going to extract some semantic information about this bus and this atlas space in order to guide the denoising process of the diffusion model towards an edit layer that will translate into a meaningful representation in the frame space. So specifically, the atlas editing step takes as input one segmentation semantic mask, one edge map, and an edit prompt, each element targeting a specific requirement that I mentioned earlier. And once the atlas editing step is done, we can query the obtained edited representation in order to edit the video frames. So the critical part here is the atlas editing step that I'm going to detail. So first, we want to extract some semantic information in this atlas space. So we take the original atlas, and we first compose it with a white image in order to increase the contrast between the actual object and the rest of the atlas. Then we pass it to a mask generator in order to locate the object that we want to edit. And we crop around this mask. So given this crop, we're going to extract two semantic information that will help us to satisfy the editing requirements mentioned earlier. So first, we extract a more precise mask M that will serve us to only edit the selected object. So this makes sure that we satisfy the minimal edit requirement. And second, we extract an edge map in order to preserve the structure of the object in the atlas space, which encodes the structural appearance and movement of the objects in the video. And this will make sure that we satisfy the realistic edit requirement in the temporal dimension. Then we pass to the actual atlas editing step. So we take the original atlas and crop at the desired location, and we perform some successive noising steps until we reach some pure Gaussian noise. Then, starting from this pure Gaussian noise, we are going to perform some successive denoising steps that are guided by both the edit prompts and the edge map. And in order to only edit the targeted region at each step, the predicted denoised image Are you in, Nicolas?
Hello. Ouais, là on revoit, on réentend. Ok, on est à la slide 27. Nous, ça a coupé la slide 27. Ok.
All right.
All right.
So we can have a look. Do you want me to go back to? Okay. So yeah.
If they didn't hear the method, then you should go back to
Okay,
Yeah.
okay, I will go back to the
because
method.
that's
Sorry,
the
sorry.
key phrase.
You heard
the key slide.
on that slide or not?
Did you hear the slide or not?
Yeah, but it was not finished. But yeah, it was not at the end. Yeah.
Okay, so you perform some successive noising steps until you obtain some pure noise, and then given this pure noise, you are going to perform some denoising steps that are guided by both the inputs text query and the edge map. So in order to only edit the targeted region, at each step, the predicted denoise image is composed with the given mask in order to only edit the region within the mask. And this ensures that at the end of the denoising steps, only the region is edited and it naturally blends with the rest of the atlas. And then we replace this image at the original location in the atlas, and we query it in order to obtain our edited frames. All right. And we can have a look at some qualitative results. So here, a car driving down a road. So I modified the background, specifically the road in this background, as a ray paved block road. Here I performed a more substantial edit, modifying both the background and the foreground into a video in Miyazaki style. Here, for example, I modified the background, which were the trees as a mountain lake. And in this video, I modified the swan as a golden swan. So now the challenge is to quantitatively measure these edits. So we can go back to our editing requirements and see how we can measure them. So the first one was the edit consistency, and we need to measure the alignment between the edited frames and the input text query. And we are going to do so in the multimodal embedding space of clip. The second requirement is the minimal edit requirements. And here we want to measure if, despite our editing, the original image content is preserved, and we are going to evaluate this fidelity in the deep embedding space of a pre-trained network, specifically the VGG network with the LPEPS metric. And finally, we want to quantify the temporal consistency. That means we want to ensure that our edit is consistent from one frame to another. So we're going to measure the similarity between two successive frames in the multimodal embedding space of the model clip. And these are the results that we obtain. So we compare the two atlas-based method, and we can see that videdit is relatively close to text to live on the semantic metrics, despite not being specifically optimized on a clip-based loss. And videdit reaches a better LPEPS metric and slightly better temporal consistency, while not being significantly cheaper to run, as it is not optimized on each target edit.
Mm-hmm.
I can test my audio.
Are you good, Stefan?
Yeah, we got disconnected again.
Yeah.
Do you want to share my slide again or not?
No, it's fine. We can see.
It's fine. It's fine.
You can see your slide.
And yeah, and we combine the strengths of atlas-based approaches with the text diffusion, text-to-image diffusion model, and we ensure that the edits in the atlas space translated into a proper edit in the video space using the right semantic controls in the atlas space. And overall, our method reaches an excellent trade-off between image distortion and edit quality. So overall, our method reaches a high temporal consistency with the atlas representations, and we are able to perform some super localized edits at a small computational edit costs. However, it requires to learn the atlas decomposition, which is quite costly and might fail sometimes, and we are quite limited in the semantic edits that we can perform due to the atlas rigidity. And finally, we depend on an off-the-shelf model with the mask generator. Okay, so in the previous section, we used different models for the generative capabilities, but interestingly, during the training phase, these models implicitly learn the semantics of the objects in an image. So starting from this, we can ask ourselves, where does the semantic image in text-to-image diffusion model, and can we repurpose them to perform zero-shot downstream tasks, such as image segmentation? So when training a diffusion model, we take one input image and we apply some noise to it. And we take this noisy input and we pass it to a diffusion model in order to predict the noise to remove to get back to a real image. And the intuition I had is we could see a diffusion unit as a stacked encoder and a noise predictor. So here we focus on the diffusion unit encoder, and I observed that the features from the last self-attention block appear highly semantic. That is, all patch representations belonging to the same semantic concept look highly similar in this PCA visualization. So therefore, we need to evaluate the level of semantic information in these visual features. And to do so, we first visualize the patch level alignment between the different vision encoders. So here, for example, we take the patch representation associated to the image of a null, denoted with the red cross, and we compute the cosine similarity between this patch and all other patches in this image. And we obtain the results on the top row. So the results we obtain with our diffusion model, SSD1B, are noticeably better than those from other foundation vision encoders. And in particular, we observe a stronger semantic coherence, meaning that patch representations belonging to the same objects are much more similar in SSD1B than in other vision encoders. And what is even more interesting is that when we compute the cosine similarity between the patch representation of the owl with the patch representations of the image of the bird, we obtain the results on the bottom row. So this indicates that our model captures cross-image semantic correspondences between semantic concepts, which is a highly desirable property for a foundation vision encoder. All right, so now we want to quantitatively evaluate these semantic coherence. So we are going to perform exactly this. We sample some pairs of patches for which we know the labels. When the labels are identical, we expect the cosine similarity to be high, and we set the target value to 1. And on the contrary, when the labels are different, we expect the cosine similarity to be low, and we set the target value to 0. So we construct a dataset like this, sampling thousands of pairs of patches to construct some RUG curves and their associated AUC. And these are the results that we obtain. So here we can see that the AUC associated to the SSD1B model is much higher than for DynaV2, which is the second best model, and which is trained specifically for representation learning. So the key takeaway here is that highly structured visual representations emerge in diffusion unit encoders. So this capacity to learn structured semantic representations opens the door to challenging problems in computer vision, such as zero-shot unsupervised image segmentation. But before difficult, a previous approach called DiffSeg addressed the task of zero-shot unsupervised image segmentation using diffusion models. And unlike our method, DiffSeg does not leverage the visual representations of the model. Instead, it focuses on the self-attention maps produced within the diffusion architecture. So the idea is to aggregate and merge information from multiple self-attention maps across the architecture and to generate a set of masks, each corresponding to a potential semantic object in the image. So in contrast, in DiffCut, we view the diffusion model as a foundation vision encoder, and we are thus interested in the visual representations of the diffusion model rather than the self-attention maps. And we're going to see the problem of image segmentation as a graph partitioning problem. So given an image, we extract some visual representations in order to construct a graph. And the idea is to segment this graph in order to exhibit some clusters that are associated to objects in the image. So first, let's have a look at the concepts of a normalized cut. So the idea of a normalized cut is, given a graph, to split this graph into two parts that are well connected internally, but have as few connections as possible between them. And what we are interested in here is to find the optimal normalized cut in the graph. So we are interested in finding a partition X with the elements of X being in the set 1 minus 1, such that this partition minimizes the n-cut value. And we are going to approximate a real-valued solution by solving this generalized eigenvalue problem. And the solution to this problem is the second smallest eigenvector. So visually, this is what happens in DiffCut. We take one input image, we extract the diffusion features, and we construct a graph by computing the cosine similarity between each pair of features in this feature map. Then we apply a min-max normalization in order to scale the values between 0 and 1. And we perform an alpha exponentiation mechanism, that is, we raise to the power alpha each element in this graph in order to pull apart nodes that are sparsely connected, while nodes that are highly connected will say relatively highly connected. And we obtain an affinity matrix W that we use in order to solve our eigensystem, and we obtain our second smallest eigenvector. And then we apply a binarization step that consists only in finding a threshold in the values of the second smallest eigenvector, such that the partition that we obtain minimizes the n-cut value. All right, so now we know how to obtain a bipartition of our graph, but we want to exhibit multiple clusters. So the idea is to perform this recursively. So we take one input image, we compute its graph, compute the normalized cut, we obtain a bipartition of the graph, and then we compare the n-cut value with a hyperparameter tau that is defined by the user. So tau is to be seen as the maximum budget allowed to perform the normalized cut. So if the n-cut is below tau, we are able to continue. So we move on the top branch and we perform the normalized cut again on this subgraph. we compare the n-cut value against the hyperparameter tau. So here, n-cut is greater than tau, so we stop here, and we store the previous partition as one final cluster. Then we move on the bottom branch, and we do this recursively until all n-cut values are greater than tau. And we obtain a segmentation of our feature map. But now we are not interested in segmenting only the feature map, but we want to segment the whole image. So how do we do this? So we take our input image, we extract the different features, compute the graph, and apply the normalized cuts. And then we apply a mask pooling operation in order to obtain a set of concepts, each describing the semantic region it is associated to. And then we perform an upsampling of the visual representations of the different mole in order to map them to the same spatial resolution as the image resolution. And to obtain our final mask, we simply take the argmax in the channel dimension, and we now know how to segment an image in a zero-shot unsupervised fashion with different features. And now what we want to... Are you with us, Stéphane? Stéphane?
Yes.
Yes, yes.
Yes.
Okay, good.
It's fine.
Yeah, now we want to quantitatively evaluate this method. So we take the SSD 1B unit encoder and we measure the MIU of the approach with fixed hyperparameters on multiple benchmarks with various levels of granularity. So for example, in the objects in the Cityscapes datasets are much more fine-grained than in Pascal book datasets. And we can see that our method significantly outperforms diffseg and also Mascot, which is based on an iterative clustering approach of self-supervised features from Dino. And we now can have a look at the effect of the hyperparameters of our method. So we can see on this graph measuring the MIOU with respect to the tau value.
Yeah. We are back. Can you hear me?
Yes.
Paul, can you hear us? Hello?
Yes.
Okay, you can hear us? We can, okay.
Yes.
We were disconnected at the end of slide 59, so I think you can switch to slide 16.
All right, and so now we can have a look at the effect of the n-cut threshold. I said that the n-cut threshold tau is to be seen as the maximum budget allowed for the normalized cuts. So the higher the tau, the deeper we can go in the recursion tree, and the finer grained the clusters we can uncover. So here, for example, when tau is 0.7, we can tell the difference between the bulbs and the light pole, whereas we can't when tau is 0.3. All right, so eventually we have seen that the semantics naturally emerge in the different modes, and we propose to see the different unit encoders as a foundation vision encoder in a computer vision task, specifically zero-shot image segmentation. And we used the recursive normalized cuts algorithm in order to control the granularity of the objects that we uncover in an image. And we apply an alpha exponentiation mechanism in order to emphasize the inter-segment dissimilarity. And this alpha exponentiation significantly enhances the robustness of our approach. So finally, our method is training-free. It requires one single inference of the diffusion model, and it is strongly robust to the chosen hyperparameters. However, it requires to solve the eigensystem multiple times, and in fact, we use a quite naive upsampling of the visual features here, bilinear upsampling. And in the next chapter, we'll see how we can come up with a less naive approach to upsample the visual representations of foundation vision encoders. So to enable efficient large-scale training of foundation vision encoders, images are typically downscaled, compressing spatial details in favor of semantic abstraction. But this loss of spatial resolution creates a bottleneck for pixel-level tasks. And in Jafar, we propose an efficient upsampling module that allows semantic features from any foundation vision encoder to be reconstructed at arbitrary resolutions. And thereby we bridge the gap between high-level semantics and fine-grained spatial details. So let's have a look at the challenges that are associated with the task of high-resolution latent upsampling. So first, the task, we take an input image, we pass it to a vision encoder, and we obtain a low-resolution feature map with a typical downscaling factor of 16. And what we want to do is to pass this image to an upsampler to map it to the same spatial resolution as the original image. So here, an upsampling factor of 16. So let's have a look at the challenges. The first one is that there is no ground truth at the original image resolution. So how do we learn our feature upsampler with the lack of such ground truth? Then we want to come up with an upsampling architecture, as what is proposed in the literature is not so satisfying to obtain high quality, high resolution outputs. And finally, we need to come up with a training objective.
Okay, sorry about the disturbances that we have. Usually it works well.
No problem.
Yeah, I also faced so many problems with Zoom today.
Okay. There is an echo on your side, Stefan, when you speak.
Yeah, now should be better, right?
Yeah, it is. Yeah.
Yeah, basically I get kicked out from my tablet. So I keep my laptop to still here, but I cannot speak with my laptop. So
Okay. Okay.
Yeah, I got the Linux update this morning and it installed a new kernel, and now my webcam and my mic is no longer working on the laptop. So I spent 1 hour and a half trying to solve the problem before the event. So I end up on the tablet.
Okay. No updates on Defense Day, but
Yeah, but
Okay, I hope we can.
All right, can you see the slides? Can you hear
Yeah.
us?
Yes, we can.
Should be good now. It should be
Should
good.
be good.
Yes, it is. It
Yes,
seems
yes.
Sorry for the interruptions.
okay.
Should be good. Up to the end.
Hopefully.
Yes,
Good.
yes.
All right, and finally, we need to come up with a training objective because how do we train this upsampler without a ground truth at the original image resolution? And given these challenges, we can define a set of properties that will help us to design our feature upsampler. So first of all, we want to be able to output arbitrary resolutions. So this is a constraint on the upsampling architecture, and this will help us to solve the lack of ground truth at image resolution problem. Then we want our architecture to be compatible with any vision encoder. And finally, we want our training objective to be task agnostic. That is, we do not want to rely on pixel level annotations from downstream tasks, such as segmentation masks. All right, but before diving straight into the approach that we proposed in Jafar, we can have a look at some previously proposed approaches. The first one is LIFT. This method is based on convolutional neural networks. So first we pass an input image to an encoder module in order to produce a representation at the same spatial resolution as the low resolution features from the foundation vision encoder. And then the two representations are concatenated at the bottleneck and further upsampled with a decoder convolutional module. The thing is, while this approach is efficient, it is only able to perform fixed upsampling ratios, and the quality of the upsampled feature maps are quite bad. The second baseline is FeatureUp, and the authors propose two different setups. The first one is an implicit formulation of the upsampler. So given one image as input, we specifically learn how to represent its high-resolution features. So to do so, we need to learn this mapping for each image separately. So this approach yields high-quality, high-resolution feature maps, but it is super computationally expensive. And the second setup is based on joint bilateral upsampling, and it generalizes to any input features from a given foundation vision encoder. However, the quality of the upsample feature maps is not as good as for the implicit setup, and it is only capable of fixed upsampling ratios. Right, so now we can have a look at the architecture that I proposed in Jafar. So we take one input image and we pass it to a shallow pixel-wise image encoder in order to map the image into a higher dimensional space from 3 channels to 128. And at the same time, this image is passed to the vision encoder in order to obtain the low-resolution semantic features that we want to upsample. All right.
Okay. Nico.
Yes, we are still there.
Okay.
Very good. Okay, so going back to the main branch, we decoupled our representation and we pass it to two encoders, one query encoder and one key encoder, on top of which we apply some adaptive pooling. So on the query branch, the adaptive pooling is here to downsample the representation to the target resolution, while on the key branch, the adaptive pooling is here to downsample the representation at the same spatial resolution as the features from the foundation vision encoder. And then we compute the similarity between the queries and the keys and apply the softmax. So for each query, we obtain a distribution of probability of the semantic feature map produced by the vision encoder. So in this sense, the softmax output can be interpreted as an interpolation kernel applied to the low resolution feature map from the foundation vision encoder. And by computing the matrix product between the attention scores and the low resolution features, we effectively generate an interpolated upsample feature map of the desired resolution. Now, considering the architecture as depicted here, as Q and K come from shallow image encodings, their interaction will tend to focus on low-level Qs. So we have queries that are low-level but high resolution, and the features that we want to upsample that are high-level but low resolution. So there is a representation mismatch between the queries and the features. So the question is now, how can we align the high-resolution queries with the semantic features? And the idea is to use a special feature transform mechanism in order to inject the semantic into the keys. So the idea is to apply a linear projection on top of the low resolution features to map them to the same embedding space as Jafar. So we extract a scaling feature map gamma f and one bias feature map beta f that we use to modulate k tilde, which is the actual output of the adaptive pooling on the key branch. So visually, this is what happens. K tilde is the actual output of the adaptive pooling on the key branch. We extract gamma f and beta f from the low resolution feature map from the vision encoder. We modulate k tilde, we obtain k, and we apply our interpolation kernel. Now the question is, how do we train this architecture? And it is in fact extremely simple, as we are able to output features at any given resolution. So given an image, we downsample this image in order to obtain a lower resolution of it, and we pass the two images to our foundation vision encoder in order to obtain one high resolution target and one low resolution feature map. Then we pass the low resolution feature map to Jafar to map it to the same spatial resolution as the target, and we align the two representations. So during training, we simulate upsampling factors up to 4, corresponding to a maximum predicted size of 64 times 64. And despite being trained on low upsampling ratios and resolutions, Jafar generalizes well to much higher scales at inference, as shown here. So here, for example, Jafar has only seen an upsampling factor of 4 during training, and it generalizes super well to upsampling factor of 16 and beyond. All right, so now we want to quantitatively evaluate our approach. So here we focus on a linear probing segmentation task, where we train a linear layer on top of the upsample visual features from a various method. So we can see that our method Jafar significantly outperforms the baseline methods, in particular FeatuP, which was the main concurrent baseline. And in addition, it is worth to notice that the bilinear baseline is already a strong baseline as it reaches the second highest scores on IDE20K and Cityscapes. And we note that this bilinear upsampling baseline corresponds to a local interpolation kernel that doesn't take the information of the input image into account. And finally, we can have a look at some results obtained on downstream tasks using different upsampling methods. We can see that Jafar produces much sharper and more detailed outputs compared to baseline methods. So for example, if you look at the segmentation mask of the bike in the second row, Jafar's output aligns almost perfectly with the ground truth, showing how well it preserves fine-grained details. And beyond segmentation or desestimation, Jafar also proved valuable for interpretability tasks, such as class activation maps. It can be used as a drop-in replacement in CAM pipelines, which are often limited by the resolution of the low resolution of the deep feature maps. All right, so to summarize, we introduced an attention-based architecture that enables flexible upsampling of low-resolution features from foundation vision encoders. And in practice, we show that training at low upsampling ratios and resolutions generalizes well to much higher scales at inference. And to achieve these, we incorporate a special feature transform mechanism that aligns the shallow representations of the upsampler with the semantics of the foundation vision encoder. So our method is lightweight. It is able to upsample at any resolution, and it produces high-quality outputs. However, so far it is quite memory intensive because each query sees all keys, and it is still backbone dependent. All right, so to conclude, in this thesis, we explore the potential of different modes as foundation modes from 3 complementary perspectives. So in the first chapter, we showed that by mapping video content onto interpretable 2D atlases, pre-trained text-to-image diffusion models can be directly applied to these structured representations. And with the right semantic guidance, they achieve video edits with impressive temporal coherence. And even though these atlas representations are quite rigid, the diffusion models show a surprising level of flexibility, adapting effectively to these 2D formats. In the second chapter, we investigated diffusion unit encoders as foundation vision encoders, and we demonstrated that highly structured visual representations naturally emerge as a byproduct of image synthesis. And they even outperform the semantic coherence of DynoV2, which is specifically trained for representation learning. So this finding suggests that the denoising objective itself is an effective signal for learning visual representations. And finally, in the third chapter, we introduce an efficient upsampling module capable of mapping low-resolution features from any foundation vision encoder to arbitrary output resolutions. So this module proves particularly useful for simplifying downstream pipelines that require a feature upsampling, and it enables zero-shot tasks such as zero-shot open vocabulary semantic segmentation when combined with vision encoders whose dense representations are aligned with text. And finally, I would like to outline some future research directions that I would have liked to explore further. The first one is an interesting direction that would decompose a video into two distinct components. So the first would be the actual content of the scene, and the second would be the motion of the objects. So this line of work would focus on the disentanglement of these two representations, allowing a fine-grained control over both the appearance and the dynamics of the objects in a video. And this could enable a highly precise and interpretable video manipulation. Second, it would be valuable to investigate more deeply the internal representations of different foundation models and understanding how these representations emerge in transformable-based architectures and whether we can make them more discriminative could provide new insights into both representation learning and generation quality. And recent studies shows that training flow-based models in the deep embedded space of foundation vision encoders improves the generative performance. And finally, a promising engineering direction would be to make Java architecture independent, backbone independent, so that a single model could adapt to any vision encoder without any retraining. So this would make the system more general and more efficient, reducing the memory usage and improving the runtime performance. And finally, overall, the representation learning framework remains largely disconnected from the generative modeling framework. However, generative modeling is theoretically well-grounded with stable training objectives, and the denoising signal provides a rich supervision source for learning meaningful visual representations. And I believe that the future of the representation learning lies in bridging the gap between these two, so developing a unified training objective to learn to generate images and to encode visual semantics in foundation vision encoders. So that's it.
Thank you, Paul, for this nice presentation. I mean, it was very dense. Yes, not a dense representation, but a dense presentation. Very clear. Easy to follow, except, I mean, like the disconnection. I'm very sorry about that, but for me, I mean, like, I think all of us really, I mean, like, get the big picture. So we are going now to pass to the second session of this exam. Question answering things, and usually traditionally we are starting with a viewer, and the first one, yes, from grown-up, certainly. I mean, like, this is Paris from here. So is Stéphane Latulière. I don't know, Stéphane, if you can hear us. Yes, we see you.
Yes. Yeah, perfect.
Hello. Okay,
Hello.
let's start
Okay, I don't see how you see me, so I cannot really adjust my.
Yeah, we
but anyway.
Yeah, it's good. It's good. Sound is good, and everything is okay. And Paul is
ready.
Yeah, he's ready. Yeah.
Thank you very much for the presentation. It was a really clear, great quality of presentation. I also really enjoyed reading the manuscript, and I really see that you put also a lot of effort in the presentation. So I really enjoyed it, despite the technical issues. And in a sense, it was also very complementary in the sense that there were some aspects that were a bit fast, because when we write, there are some details that are take space to explain. And here, you really took your time to explain what was required to understand your contributions. So thank you very much for this. Then about the technical work itself, the scientific quality of the work, it's also really great. I really enjoyed the three chapters that you presented. So they are somehow tightly connected, but still on very different problems where you have different competitors, specific literature to understand. And I think all these contributions are really well positioned with respect to state of the art. But so I still have some question, and so I will go chapter after chapter, starting from the video editing part. So you treat here this idea of using atlases. So it's quite original because I think in the video editing literature, there are not so many works that have this way of seeing editing in a interpretable way, right? We really understand what's going on, how the model separates the different objects in order to edit. Most of the approaches, and I think the most popular approaches now, are kind of, they don't really try to bring this inductive bias that you try to put through atlases.
Yeah.
If we just care about edit quality and we don't really care about interpretability that you clearly bring also with this atlas-based method, do you think the future is more in a kind of data agnostic way, just pure, learning-based approach? I'm asking the question because we see here it's video editing, but we can think about many other tasks where basically forgetting about what is an image, just seeing them as tokens, and then doing it blindly turn out to be better. Do you think it's the same for video editing?
Oh, sorry, I think I didn't understand the question.
So basically, for many problems, not video editing, we see now that the best approach is not to bring some inductive bias through the the architecture that we use. Here for video editing, you actually really impose that you want to decompose a scene and then do editing for object, while other approaches are more they don't care about distinguishing objects, they just manipulate attention map through the different layers. Do you think that putting this objectness into the editing approach is what we should do?
No, I don't think so. I think the atlas representations are too rigid to perform. I mean, it encodes the temporal constancy super well because you have you query directly these atlas representations. This is good, but you're bounded to short videos because you cannot map too long videos into these 2D representations. Otherwise, they are not interpretable anymore. So I think the future lies into scale models, scale generative models, where you can have a fine-grained control over the attention maps or the visual representations of the model to perform editing. So, for example, modifying directly the attention maps with an input text prompt, or So I think the future does not lie in the atlas representations for video editing.
But you still see some cases where atlases would perform better, even on longer term.
In the long run, I do not really see a future in atlas representations, as it is extremely rigid to perform some edits in these spaces. As I said earlier in the presentation, we cannot perform substantial semantic edits in these spaces because the atlas representations encode the movements and the structural appearance of the objects in the video space. So to perform more substantial edits, it would be better to get rid of these representations.
Okay, thank you. So the first step of this approach is estimating the atlases. So you use an existing approach for that. What is the quality of this atlas estimation? Do you think this is somehow the bottleneck of your approach, or in the end it's not really, just more the editing part that matters?
The atlas representation is definitely a bottleneck of the method because sometimes it might fail. It might fail, especially when you have some objects that rotate in the video. So you have the same points that appear multiple times. So you need to have a tracker on this point. So remembering how it is done, you need to have to estimate the optical flow of the video in order to obtain an atlas decomposition. And so when you have multiple points that appear multiple times, it is hard to get some semantically meaningful and interpretable representations.
I see.
So, yeah.
I see. Actually, I was checking that basically this layer neural atlases that you used is from 2021, right? So quite old at the general speed of the community. And I wonder if there is, with the development of diffusion-based approaches, if it wouldn't be possible to improve this stage also. What do you think?
You mean improving the atlas decomposition?
Yeah, itself. Yeah.
Itself. Yeah. I think there are potential ways to improve this atlas decomposition, but I'm not sure that this would be the best. I think the future more lies in the scaling of the model, training a better model with better how to say interpretability in the feature maps, better discriminability in the visual features of the deep models, because it would enhance the comprehension of the model itself, but also the comprehension for representation learning, vision and colors. So I think yeah.
Okay, thanks, very clear. So that's it for the first part that you presented. Now we can maybe move to DiffCut.
Yeah.
So you had a very nice slide where you showed the iterative process where you segment iteration after iteration with remaining part of your graph. I don't know if you can go to this slide.
Sure. Sorry.
No worries.
This one?
Yeah. So basically here you proceed iteratively, right? So you have some object that will be segmented first, right? And then the others.
To be precise, it is recursively because there is another approach called the mascots that performs it iteratively, and you cannot segment objects that have been already segmented. So I mean, the difference is that here is that you can segment. So you obtain a bipartition, and then you can partition again some clusters. And iteratively, I would say it is like you obtain a bipartition, and once that you have a subpartition, you cannot. You will mask you will mask the objects, and then obtain a subgraph and partition the subgraph the other region. I'm not very clear. Okay. Okay. I will put it differently. So you iteratively you have you perform a bipartition of the graph. You identify you need to come up with a heuristic to decide what is the object, the actual object. Then you move it aside, and then you focus on the rest of the atlas, and you cannot segment again the object that you identified.
Okay.
So this is the mascot approach.
Okay. Okay. Because I was asking, do you see any different on what kind of object appears first? But in this case, the question doesn't make sense, right? Does it? When you do it, what you call recursively, still you could.
The objects that appear first are the I don't know how to say it in English, but silent object, the most silent objects in the image in the image. So it might be the first objects on the foreground. For example, in the previous graph partition image. So here this was the bird. And
are they really salient in terms of colors or more semantically? Because I guess it operates in a feature space where basically you could have a red bus on top of a red background, but clearly semantically it's very salient. Why different trees, even if one has orange leaves and the other one green, semantically they are not salient. You see what I mean?
I mean, it's salient semantically in the feature map.
Yeah.
This is why this works so well, because you have a clear semantic coherence in the features of the diffusion model. So each object appears as let's say all patch representations of a single object look very similar. So given this semantic coherence, the silent objects are semantically silent. Yeah.
Yeah, you mentioned also this idea of fine grain. I think for one of the data set where you say in this data set annotation are more fine grain. So I don't know if it was in terms of segmentation or in terms of classes. But do you see also specific behavior of your method on this in terms of fine grain, in terms of segmentation or in terms of semantics?
In terms of, I mean, I would say both are connected. Like when you allow the tau value to be higher, so you will get smaller clusters because you subpartition the graph, and you focus on a subpart of objects you already uncovered. So so for example, let's say that you have an image of a car. So you put the threshold 2.3. Let's say that you will uncover the whole car, and you stop it. And then if you set the threshold higher, you allow to uncover some parts of the car, for example, the window, the windshield. I don't know, stuff like this. So these are also semantic concepts.
Yeah, true.
So you have a more fine-grained segmentation of the image with the semantic concept.
I see. I had also a very general question here, because so basically you're addressing a problem of unsupervised segmentation. On the other side, we see a lot of literature on how to scale supervised segmentation with work like SAM and the hundreds of variants that came out from SAM.
Yeah.
In your opinion, what is the role of all these works on unsupervised segmentation? Is it to provide a kind of pre-training, or do you think that at some point we will be able to do fully unsupervised and still outperform when they supervise, or what is your understanding, or what would be your guess for the long run?
I mean, unsupervised segmentation is hard, and it is so far it is quite expensive to do. So, for example, here the main bottleneck in the approach is that you need to solve the eigensystem multiple times, which is quite costly when you want to exhibit like multiple clusters. So, in my experiments, the runtime was, let's say, a second for an image of size 1024 times 1024, but with the correct tau value, because if you set the tau value to super high values, it can go up to 1 minute or more. So this becomes quickly intractable. So I would say that so far the best approach is like to use some supervised method like SAM, but exploring unsupervised segmentation approaches gives like new insights into the disentanglement of the features of the foundation vision cars. I mean, in the long run, the best way is to perform, of course, unsupervised image segmentation, because you do not want to rely on pixel level annotations from annotators, because it is extremely costly. But I'm not sure this. So far, I don't see an approach that is sufficiently performance doing it in an unsupervised fashion so far.
Actually, I'm not that sure, in the sense that if we think about what happened for image classification, at some point everybody was using supervised feature trained on ImageNet, but now we know that unsupervised features that are trained in an unsupervised manner usually more robust, right? We could also imagine similar outcome for segmentation, except that here you're working on frozen features, right? But maybe on the long term, unsupervised segmentation methods could turn out to be more robust than supervised. I don't know, no idea how we could reach that point, but
I mean, the first step would be to come up with an algorithm that is as efficient as for the supervised manner.
Yeah. If we want to scale at some point, compute.
Yeah, exactly.
Okay, let's move on maybe to the last chapter because I don't want to take all the time for my questions. So you didn't take much the architecture for the high resolution encoder, the image encoder. I wonder what is a typical architecture you use and what is I mean, I guess you keep the same resolution, right? So you don't want to have an encoder that is too large, right? Otherwise compute becomes prohibitive, right?
You mean for the image encoder?
Yes.
Yes, this is a shallow MLP, so this is just like a res block with the overall size of the architecture is like 700K parameters. So this is very, very shallow encoders.
I see. And I guess you try a bit more and it doesn't bring anything.
Yeah.
Okay. And also, I was wondering, you have this SFT that you introduced to get some. Can you tell a bit more on the impact of this SFT on the quality of the super resolution you get?
Yeah, sure. So the idea is that when you don't have this SFT, so this corresponds to this. As you have only a shallow encoding of the image, so the interaction between the queries and the keys focus more on low-level cues such as colors and textures. Okay, and so this is this works to some extent. So, for example, if you look only in a nearby region, so if each key looks only in a nearby region of itself, this might be sufficient. But here each query looks at all keys. So you have the attention is spread across a large number of features. And what we want to do is to constrain you want to constrain a bit more by guiding the attention with by introducing the semantics of the features. And okay, maybe I have some.
But actually, it's related to the second point you were mentioning. I think in the very last slide, there's a future work. The idea of making this work encoder agnostic, right? It could work for any architecture. If you don't have this SFT, if I understand well, your softmax, your attention map could be used for any vision encoder, right?
Yes, exactly. Yeah. Maybe I can talk about an ablation of the SFT if you want to describe a bit how this behaves. So for example, here this is an ablation. So this is a global attention mechanism. So we remove the SFT mechanism and we evaluate the approach without it, and it underperforms slightly the SFT approach on VOC and AD20K, but largely on CT-scale. So when you need to upsample fine-grained clusters, this is much harder when you do not have the semantics. But the way to go, so I have performed some tests with a local attention mechanism. So each query sees only in the neighborhood of itself. So you downsample the queries, and each query will look in the neighborhood of itself in the downsample keys. I don't know if it makes really much sense, but let's assume that you have a special correspondence between the two, the high resolution queries and the low resolution keys. And in fact, you can remove the SFT mechanism and obtain some pretty decent scores that are almost on par with the SFT approach.
Okay, I see.
There is,
please.
sorry. There is a recent work that improves on our paper that is called AnyUp that shows some stuff like this. Like basically, you could remove the conditioning with a local attention mechanism.
I see. Yeah, and I was wondering also this attention map you compute, and then you could apply it even on different features, even if you compute it with Dino through this SFT.
Yeah.
And you could also apply it on the image itself, right? Or just to see if your method makes sense in terms of do you really get this the original image if you super
if you want to perform super
resolution of the image itself. I mean, the question is somehow if we compute an attention map to do super resolution of the Dino feature, but we apply it on the image, do we still get the same? Or is it really a different map that we should use to the super resolution of Dino feature and super resolution of the images? Is there really something specific in Dino feature that the interpolation we need to operate is different from what we would do with images?
Honestly, no. I think it could probably work to perform super resolution on images.
I think it doesn't make sense, right? Because you have the already initial image, right? It just to understand what this super resolution is doing. Right?
You could think of a way of doing a super resolution by upsampling the latent of a VAE. So you have your VAE, you get the latent, and you try to upsample it to obtain a high resolution version of it, and then to pass it to the decoder, and in this way you could perform the super resolution. I'm not sure that this would work. This is a hypothesis. I'm not sure this would work really well, but this is one potential way to perform a super resolution.
I see. Okay, thank you. Thank you very much. I have maybe one last question about the future work. So you presented some future work, let's say one per chapter. Now, if you want to step back and see, so you have very different areas of research, right? Video editing, super, like really feature, super resolution segmentation. If you want to start a PhD, maybe as a supervisor now, with going into a field that is, will be open for 3 years, what would be the one of the 3 area of research that you would pick, and why?
I would pick something on representation learning. So something at the intersection between the diffcut and it would be probably based on what I experienced in diffcut. So bringing the denoising objective in the latent space, some sort of doing like a diffusion JPA, like you try to bring the diffusion objective in the latent space to see if it transfer well, if you get a better structural representations with this denoising object. I mean, we have plenty of methods that work quite well to generate images, and I don't see why we do not apply them in the latent space to learn some representations. So this would be my way to go.
Okay, interesting. Thanks a lot.
Thank you very much.
Okay, thank you, Stéphane, for your questions. And let's continue. I mean, like with the second reviewer, Frédéric. Frédéric, the floor is yours.
Thank you, Mathieu. Thank you, Paul, for the presentation, which I enjoyed very much. Before I ask my question, I would like to say how much I enjoyed reading your manuscript. And I found that your work is a very high quality piece of work, mainly because I think it addresses a central and very timely and important problem in our field, which is now that we have these foundation models, how can we use them for complex tasks that require a deep understanding of visual scenes, and I think you brought interesting contributions to this topic. I also enjoy the structure of your manuscript. The contributions follow one another in a very logical way, I think, and from video editing, segmentation, and then the limitation of their low spatial resolution. So I think it makes a coherent piece of work. And also something that I appreciated is your ability to combine modern deep learning techniques, foundation models, etc., with well-established older computer vision concepts like combining generative models with normalized cuts. I think it's clever, and it shows that you know more than the latest trends of the field, which is interesting. And the focus on zero shot also is interesting because obviously the less annotation you need, the best it is. So this is not only efficient, but it's also practical in terms of application. And and obviously you have been able to present your work in top-tier conferences and journals, which is very good. Okay, so I can, however, ask some questions. Yeah, maybe my first question. Well, I would have two general questions and maybe some more specific ones. Maybe the first one is related to the zero shot term you are using in your presentation and in your manuscript. In fact, can we really call this method zero shot because they have seen so many images and so many annotations? So do you think that it's appropriate to call them zero shot, or should we use something else?
Okay, the model has seen images with the associated captions. So I use zero shot to say that the method doesn't see any annotation, any mask, annotation mask, and so I use the zero shot word to design the mask that's a model would see. So in this way, the model is completely zero shot because it has never seen a segmentation annotation.
Yeah, so zero shot in the sense that you might have some annotations, but they are of different natures than the problems you're considering. But okay, but still there are some annotations in the process. Okay. Maybe the strongest limitation or the frustration I had while reading your manuscript is that you are talking a lot about the successes, what works, to which extent it beat other methods. But I would have been also interested by the failure cases, because it could show also I mean, the limitations, what is possible, not possible. And I know that because I've already experienced such method, I know that if you move slightly from the type of images you usually find on the internet, for example, if you start using very application-oriented images as those that are usually involved in Thales applications, then the performance will decrease very quickly. For instance, if you use infrared images or any kind of spatial images, because they are not very frequent in the training sets. Can you comment on that? Have you made experiments on more challenging tasks in the sense that more different than, I mean, than common task, common types of images you would find on the internet?
So this is quite disappointing, but no, I didn't perform extended evaluations on out of distribution images. But this is one limitation of the approach. You're bounded by the distribution of images that the model has seen during training. So yes, as you said, most likely the method would not perform as well on out of distribution images, such as medical images, or I don't know, bird eye view images. So yeah, this is something that was asked by a reviewer at the conference. So yeah, this is if you want, most likely, if you want to keep the same level of performance, the model should at least be fine-tuned on the target's data distribution. Yeah.
Yeah, I think it would be interesting to do these experiments, at least I mean, specific domains to see how it behaves after fine-tuning. Is it, I mean, because it's possible that fine-tuning will destroy the latent representation,
Yeah.
The separations of the concepts, or I mean, many things are different after fine-tuning. So that would be interesting to see at least what are the limitations.
Yes.
Have you seen any other limitations? Because you are not talking about limitations in your work. I'm sure there are. So
Yeah. I would say that you need to the first thing that you need to in order to run this method is to come up with a good layer in terms of representations. And this is this is something that is quite intuitive in unit architectures, because obviously you have a special compression of the visual information. So most likely the semantics will emerge at the bottleneck of the architecture. But this is not so intuitive when you work with, let's say, transformer-based architecture, where you do not have this special compression. And so you would most likely need to go layer by layer and to see which one is the best to perform this task. So in this sense, this is one single limitation. If you want to extend the approach to transformer-based architecture, that have been scaled to another level, and this is not so evident because I have read a paper recently where the authors claim that while some layers are semantically meaningful, some other only reorganize the information within the network, and so you have very little semantic information in these layers. So the approach would most likely completely fail if you use it on the wrong layers, wrong representations. And the second one, you need to tune the hyperparameters to in a, let's say, in a clever way, or non-degenerate way, because otherwise you don't segment the image at all, or the method will run forever just to output one single mask.
okay, I see. My second general question, I don't know if it's a question for you. At least it's a question I'm asking to myself. If you have any feedback on it, I would be happy. It's a difficult question. I'm not sure there is any answer, but I would be happy to hear you about this topic.
Sure.
At the beginning of the computer vision history, I mean, people were designing algorithms to extract edges, regions, etc., to compute the 3D geometry of scenes. And then it has been absorbed by the learned models. And so these models are doing more and more things themselves.
Yep.
Especially now you have foundation models. You can ask them to detect objects by prompting them. And if you look at the recent advances of Google with Alpha Evolve, it's even possible to ask these models to build algorithms as long as you are able to give them any metrics or any way to see if they go to the right directions.
Yep.
And so my question, I guess you see where I'm arriving. Do you think that it's still necessary to design algorithm as you are doing in your manuscript, or are we reaching a step, a moment where designing ourselves algorithm is not relevant anymore? But if you have, as I said, if you have a kind of loss function, a way to evaluate the performance of the algorithm, would it be possible to simply ask Alpha Evolve to address the problems you are interested in? Do you see my point? You are building on very sophisticated tools, but maybe these tools, they can do even more, and they can do what you are trying to do by additional steps. They can do it. They can do them directly themselves.
Right. Honestly, I don't know. I don't know Alpha Evolve. Is it some sort of reinforcement learning, or during training, or this is at inference time, or where you have multiple steps that
Well,
refine?
basically, you use agent, LLM based agent. One is producing algorithm, another one is evaluating the algorithm and trying to help the first one to build better algorithm, and then it's iterating. And as long as the process goes, then the algorithms become better and better.
Okay. Okay. So you need to have and you need to the agent needs to have a metric in order to
Exactly.
evaluate.
Exactly.
Okay.
Well, I
Honestly,
would say there is probably no answer for the moment, but I don't know if you have any comment on this. If you don't have, it's not a problem.
honestly, I'm not so don't have many ideas on the topic. I'm
Okay,
sorry.
no problem, no problem. Well, in my report, I pointed out some points for discussion, but I think that we are having less and less time, so maybe I can pick a few of them. During your presentation, I was wondering when you use the variational autoencoder in your diffcut method.
Yeah.
I guess there is I mean the size of the patches of the latent representation is important. Is it? I mean, is it something hard to fix? Is it very dependent? Because I think if you take very small, I mean too large patches, then their semantics could be probably too low, and if it's too small, maybe it's very rich, but spatially, I mean, too vague.
Yeah.
Yeah. So is it something very sensitive, the size of the patches of the
So yeah. So you have in the model I used the patch size was so you have a factor of 8 between the original image and the latent that you get in output, and then you once you pass this latent to the unit to extract the features at the bottleneck. You again have a compression factor of I think it's 4. So overall, this is a 32-fold compression factor. So you need to have a large input size, large image sizes as inputs in order to to be able to construct a segmentation map that is meaningful. So I'd say that 1024 was probably the minimum size input image size that you could use in order to run the difficult algorithm. So this is one critical.
Is it a critical hyperparameter, or is it something you take the autoencoder off the shelf and use it as it was, or did you struggle to find the right hyperparameter?
No. I used the VAE off the shelf. I didn't touch the hyperparameters, but there is a trade-off between the features that you get as inputs and the runtime of the method. So the larger your feature map, the longer it will run, and the more expensive it will be because you have a super large graph.
Okay, I see. Another question I had regarding the hyperparameters is the threshold. It's for the zero-shot semantic segmentation. And you call it, I think, tau in your manuscript. It's the threshold for terminating the NCut process.
Yeah.
How do you fix this threshold?
So in my evaluations, I set it to I think it was 0.5 for all benchmarks. So now I imagine the question is why 0.5 and not like 5 or some other random values?
Why choosing the threshold versus, I don't know, the number of component or whatever, or the size of the component, or?
Yeah, so if we wanted to come up with an approach where you do not fix the number of objects you want to uncover in the image beforehand. So and the threshold was quite nice because this is something that lets you control let's say the size of the object that you want to uncover. So if you set it low, you will uncover some large objects, and you set it high, you will obtain super fine-grained clusters. And now, in order to find a good range of value, you obviously need to perform some tests on the feature maps themselves. And if you change if you go from one model to another, for example, we performed some tests on SD 1.4, which was one early version of Stable Diffusion. The value of the tau is not the same. So yeah. Ideally, what you have is so you will not go you'll not be in the zero-shot setup again, but you allow yourself to have a small data sets of images on which you can fine-tune your tau, and this way you can have the optimal value to obtain some good results.
I see. Okay, thank you. Maybe one last question regarding Jafar. As far as I remember, Jafar is designed to be task and backbone agnostic, but however, you have to train it separately for each backbone. Am I correct?
Yeah, right. This is correct.
And do you see, so it's kind of limitation of the method. Do you think that it's possible to find a way to have something that would be really, generic in the sense that it would not require any specific training?
Yes. Specific training. You mean for each backbone? Yeah. So as I said, we performed some tests using a local attention mechanism. So each query only sees a neighborhood of the keys, assuming that you have a special association between the high resolution queries and the low resolution keys. And in this sense, you have a much more focused attention map. And in this way, you can still have a good performance without having to use the modulation approach. So basically, the limiting factor here is the modulation mechanism, the SFT mechanism. And if you use a local attention mechanism, you could basically get rid of it and have an architecture that will translate to any vision encoder in a zero-shot fashion.
Okay, thank you. Maybe one last very quick question. Just to be sure, in the Jafar approach, the decoder you use for producing the okay, no. No, sorry. No, my question is not relevant. So, I'm going to stop here. Thank you for the presentation. Thank you for answering my questions, and also thank you for you and your advisor for inviting me to this jury. It was a pleasure to be here. Thank you.
Thank you very much.
Thank you, Frédéric, for your question. And let's continue now after the reviewer by the examiner. So I don't see Alex. I mean, perhaps you can just move the things. You want to see Alex somewhere? Yes.
Yes.
Okay, Alex, thank you. And the floor is yours.
Thank you also. I'm not gonna repeat all the positive comment, but I want to congratulate you. Really a great work. It's really impressive. In interest of time, I try to go quickly to the questions. Maybe I'll start from the end, and if I have time, I go to the first one.
Yeah.
Yes, so I guess I think slide 70.
Yeah.
Yeah, if you go to
this one.
So you had a slide with the performance of the quantitative result.
Oh yeah.
Sorry, maybe 71 then, I don't 76, sorry, 76, yes. And it's true that when I was thinking about this task, very quickly the naive methods of nearest and bilinear interpolation came into my mind. And I'm happy that you put them in this quantitative result and qualitative result. I think if you can stay in the 76.
Yes.
Yeah, sorry.
But then, yes, when we look at the numbers, at least quantitatively, it's not very very different. Do you have? Can you say something about that? I mean, like I mean, there is a lot of overhead to develop all these, but the simple bilinear.
Yeah. I agree. The banner baseline is already a very, very strong baseline.
What line is it? Can you say just
the second one? The second one is a banner baseline.
Okay. Wait, Alex, because we have your face.
Oh, sorry.
Above the slide, but okay, so.
Should I remove my camera?
Yes, we can ask to the Atlas things to do something, but okay, it seems better. No, me. Voilà. Yes, fantastic. Thank you.
Yeah, so the binary baseline is already a very strong baseline. So, for example, it beats lift on all benchmarks. So yeah.
And I guess lift never compared to this baseline, right? In the paper.
I mean, lift doesn't even do semantic segmentation tasks. It only evaluates on keyport matching, and I think there is a reason behind it.
No, but I think often we don't do the simple baselines, and we jump into this complicated method, or I mean.
I mean, okay, maybe in the task of when you want to train specifically an upsampler in an end-to-end architecture, Jafar might not be the best, the optimal choice in terms of runtime performance. For example, because you have a lot of computational overhead. However, what in the tasks such as zero-shot open vocabulary semantic segmentation, for example, with a Dino v3 aligned with text, this might be super useful because you can perform the tasks just like this. So you have your low resolution feature map, you have sampled the feature map, and
Yeah,
then
but I can do it with bilinear, right?
yeah, but you will have a less precise segmentation mask because bilinear of something. So you don't take the information of the image as input, and so you'll have a segmentation mask, but quite coarse around the objects that you segment.
But I mean at 0.68% difference or
So I mean I don't know. So I didn't evaluated it on Dino V3 zero shot segmentation. But here this is a linear probability segmentation. So I mean this is something we should evaluate to. But yeah.
I guess my what I was maybe expecting as an answer is when we look at your qualitative result, we see clearly a difference. But with
Yeah.
respect to the number of pixel, it's very small, but they make a difference, right? So statistically, if you this metric average over the whole image, right?
Yeah.
Pixel size. So then you will not see a huge quantitative difference, but when if you show your, I guess your next slide qualitatively, then the argument is much stronger.
Yeah. Right.
But then indeed the difference in terms of the number of pixels between these two examples is maybe negligible. I mean compared to the size of the image. So that's
Yeah.
why your quantitative number might not be the most reliable metric. Maybe this was what I was expecting. I don't know if my intuition is correct.
No. I think this is correct intuition, and maybe with some higher upsampling ratios, the difference would be more significant.
Right. But then, so I guess my follow-up question is, indeed, when I look at the bilinear interpolation, then again, other interpolation technique come into my mind that are a bit more advanced than bilinear, but they are, standard super resolution technique, independent to all the things that you do. I mean, do you think that they will potentially even improve the baseline? In the field of interpolation, and you will have a lot of methods. And definitely, sorry.
So using interpolation and the diffusion maps of foundation vision color.
Right now, you use baselines that are even not learning-based method, right? A nearest neighbor or a bilinear. I mean,
Yeah.
but there are also other techniques a bit more advanced to do super resolution that do not require having something specific to learning based on this vision encoder, right? I mean, whatever Jafar is doing.
Yeah. We did not try all methods that can perform the upsampling in a learning-free fashion.
Exactly. Yeah, that's the question.
No. We only evaluated nearest and bilinear.
But don't you think that in fact you will basically reduce the gap or potentially match the performance of Jafar, or if we just change the learning free interpolation method?
No, never.
Okay. Maybe then I'll go to the second work.
Yeah, sure.
And I guess it's also related to the first one a bit. But your the whole motivation. I mean, when you started your presentation, you put forward these foundation models and focusing on foundation models for vision encoder, right?
Yeah.
So I was expecting, for instance, for that you made most of your experiment are potentially changing this foundation model with respect to what you're doing.
Yeah.
But I did not. But are you doing it, for instance, for the second work? So the second work, have you looked at maybe I don't know what slide? Yes, for instance, here you pick one backbone.
Yeah.
But then did you change it? Did you like look at which foundation model has an impact on this?
Yes, so I have a slide evaluating the impact of the backbone. I don't know where this is. Maybe this, yeah. So here, for example, we modified the backbone and evaluated the method with so stable diffusion 1.4 SSD Vega, which is a smaller version of stable SSD 1B, and we see consistent gains over DivSeg, which was the main concurrent baseline, and we see that so SD 1.4 is a lower, a much smaller version, a less scaled version than SSD 1B. So you have you have gains, but not as much as for SSD Vega and SSD 1B. So the gains are we observe the gains on all different molds, and especially on the scale molds. And then we try to
Okay.
we try to change we try to perform this approach with with the Dino V2 features, for example, and the results were not as good as for the stable diffusion model.
So in fact, this was what I was asking, like Dino or MAE or this other type of vision.
Yeah, right. Okay, so for example, the MAE encoder, the features of the MAE encoder are not so semantic because they are targeting pixel reconstruction. So the semantics, as shown in one of the early slides, so for example here, are not so semantic. So I think the results would be pretty bad on the MAE approach. And then for Dino V2, for example, you can see that there are lots of artifacts in the feature maps. This might hinder the approach to perform high quality segmentation masks.
But I guess this is exactly the slide that maybe misled me. So I was expecting, I mean, expecting to potentially that you tell me which of these vision encoder is good for, but you're not comparing them explicitly.
No, I'm not comparing them explicitly. This would be
but this is what you said in the intro, I think, or I misheard you. You said these encoders exist, and I'm gonna basically.
Yeah, right. So in the second part, yeah, we could have evaluated diffcut on these different. I mean, providing an evaluation on these different vision encoders. But for example, the discriminate, how to say it. Some features are not so semantic. So when you evaluate some on.
I certainly agree with you, but do you have quantitative metric, or do you have experiments supporting these intuitions?
I do not have them here, but if you, I did them on. I tried these vision encoders before going to the SSD1B method, and they were underperforming the different approach.
I see, but I see. Okay, but I think, well, I don't know, but this, this will help. This is actually very interesting, as a study.
And I think this is what I tried to show with the, the rock curves and the AUC. What was it? Yes. So here, for example.
Exactly. So sometimes, indeed, you do it, but
yeah, all right.
but
Okay.
it was not consistent for the whole line of work, whereas the introduction was really putting this forward. So I was, but like for instance, in the first part, there is not such a thing, right?
Which first part?
I mean, your first work on video editing.
Oh yeah, no, there is no such.
I mean, it's not even about vision encoders or.
No, it's about using the different model in a zero-shot video editing tasks.
Right, exactly. So it's like using it in a way that people did not use it before, right?
Yeah, Yeah, exactly.
Yeah, absolutely. But I think to me, it was a bit of a mismatch with the motivation. And suddenly when you presented the first work, I'm like, but how is it connected to actually studying foundation vision encoders?
Yeah, right. So this was to see if different models could be used on tasks that were not being trained for. So, for example, your different model is trained to perform image generation, and the idea was to see could it be adopted for a task of zero-shot text-to-video editing on an atlas representation space, which is absolutely not the what the model has been trained for. And,
right. But then you tried and it worked, right? So you wanted to show that this is possible. Yes. Yeah.
And the representations are flexible. The model is flexible enough to adapt to completely out of distribution tasks.
But how do we know it's out of distribution?
Because the images, the representation in the atlas space are not in the distribution of real images. The model.
No, but do you have access to the training data of these models? That do you know if they have also?
So we used SD1 Stable Diffusion 1.5, I think, and the training data was a Lion.
Okay, so they communicated the training data and it's transparent. Okay.
Exactly.
Yeah, super cool. I guess yes, I will stop here. But thank you again for all this fantastic.
Thank you very much.
Okay, thank you, Alex, for your comments and questions. Let's come back to in the room. I mean, like with real people asking questions. In the real room. Okay, so let Vicky first, please. The floor is yours.
Thank you, Mr. President, and thanks, Paul, for the very clear presentation, the very good manuscript, the great work. It was a pleasure listening to your talk, and the structure and everything was very captivating.
Thank you very much.
I will hopefully be brief, similar to Alex. So first, in one of your answers, perhaps to Stefan, you said what you would do now. He said work one was 2021 based on Atlas. Good. If you were to do that today, what would you do? And you answered in summary, scale.
Yeah.
Do you think that the solution is scale up data and compute? And if so, what is left for academia?
I think what is left to academia is coming with more clever way to train models, especially different models. So you have like huge architectures to train some different models, and maybe you could. One idea I would like to try is to come up with some better way to train these models. So, for example, warm up some of the layers, some of the outermost layers, and then progressively add some layers in the architecture. So that at the beginning of the training, it learns some general representations, and then you come up with new blocks with the residual connections in order to have a fine behavior during training. And then, the objective eventually is to reduce significantly the cost of training such architectures.
Okay. So essentially, you're saying that there is something orthogonal or complementary, let's say, to scale.
Yeah,
that is actually efficiency.
Yeah, definitely.
Okay. So
this joins the work, the representation of truncated work, where you have seen that you can obtain the same FID metric with 40 times less compute if you were training in the deep feature space of Dino instead of a pre-trained VAE. So yeah.
Okay, and you think that efficiency in this case, so I follow up on this, is via representation. One of the ways, perhaps not the only way, to make more efficient foundation models is via exploiting better representations.
Yeah.
Okay, and what is okay? Pause on that parallel question so that I will combine the two after. Have you at all looked at, or are you aware of this unification of generation and representation, like this new type of work that you have tokens that do both?
So I never tried it. I think this is so far. I think this is the way to go. So I haven't seen some work that's. Oh yeah, no. So actually, yeah, I've seen one work at iClear 25, where they were training a JPA with a diffusion denoising objective. But the main focus of the paper was for image generation. And in some of the experiments, they were saying that you could also use your model as a vision encoder. So this was targeting the both tasks. And I think this is the first paper that is doing this, and I would like to dig more on this because to bridge the gap, there is super interesting advancements in generation quality and the sampling steps, how you train your architecture that is completely disconnected of the representation learning approaches so far. For example, Dino, which is disconnected of it.
25 or 26?
25.
26 not out?
Yes, submitted. Yes.
No, the paper is called Denoising JPA.
Okay, so combining the two. So I understand what you're saying. So for you, if I may say my understanding, for you, representation can be learned from self-supervised learning. Therefore, you mentioning JPA, and you think that basically combining representation and diffusion, or generative basically modeling, would be one of the steps forward.
This is one idea I would like to try next.
Okay.
Combining the two, yeah.
Okay, and on that scheme, like if you think of a 5-year window, like you, the community, or whatever you can think of, there, when do you see emerging?
I see emerging. So first of all, the complete abandon of the Dino. I think the object. I mean, in Dino v3, for example, there is very few insights into how semantics is learned in a model. So they have scaled the model as far as they could with tremendous GPU hours, but it's not that convincing because they didn't even provide a clue on why they need to add another loss on top of all Dino losses, because they see that the longer you train, the better the representation, the worse the dense representations are. So I think the discriminative objective of Dino is not the way to go. Whereas, as I try to show with my work, is that when you try to perform an image synthesis task, then clean semantic maps naturally emerge in the architecture. So this is why I think bringing this objective in the latent space, because we know that bringing it in the latent space favors the semantic abstraction, would provide a better architecture with probably more semantic disentanglement. So yeah, in the 5 years, I say I will see more works that are targeting this specific axis.
Okay, so to follow up on the 3 last things you said, latent, abstraction, and disentanglement.
Yeah.
Latent. So I assume that if you were to do VDD today, you would operate on the latent space, on a latent space anyway, instead of Atlas. Yeah. To my understanding, at that time you were keen on working on Atlas and whatever it would offer, but today you find it more rigid. Is this correct?
Yes, exactly. Yeah.
Okay. So with respect to this about the latent thing, I think that this connects all your works, like you trying to understand some emerging patterns, latent representations. My question for that would be on your second work, same for the third, but what about affine transformations? Also for the first, actually, like your videos, some of the videos, I think that they are coming from Davis or whatever, like this one, it doesn't really move, right?
Yeah, because this is one of the main drawback of the Atlas representation. So you cannot have, as I said, you cannot have objects that move too quickly or rotating in the video, because otherwise the Atlas representation is not semantically meaningful anymore, and you cannot edit the videos as well.
So for this, do you think that, for instance, your second work or your third work would what is your intuition that it will work for affine transformations, scale rotation specifically, if you want shear or whatever translation, but scale rotation specifically.
How will it work for such a?
Like you have a, I don't know, like this, and you have it like much smaller and moving my hand, and you have it much smaller and moving in time. I was like, do you think that the covariance is there? Do you think that you said that basically there are emergent patterns, and this was one of your properties that you defined in the beginning as you call it spatially coherent, I think. You said about lift that they may or may not do that, about the point matching in this case.
Yeah. So sorry.
Okay, let's say. Do you think that if you had affine transformations, you have your image, you scale it down, or you have your object, you keep your image as this, and you scale down the object? Do you think that the emergent features that you have at any point would they work?
I think this would work.
So it's equivalent to this type of affine transformations, scale and rotation specifically.
I mean, we hope so.
Okay. And do you have an intuition as to why?
Because you're supposed to encode the semantics of the image.
Okay.
Right? So if you encode the semantics, you know that despite the scale, you're supposed to have the association between the two.
It's the same for diffusion, though, and if diffusion doesn't encode, if generative model doesn't encode semantics.
No, they do.
Yeah. Okay. Right. I mean that this is one of the challenges. I think that's anyway for me that will be an interesting thing to
yes, definitely.
I guess also on your maybe other category of things is that of your work, it combines again work 2, 3, and maybe one of the questions of Alex, and maybe your efficiency answer is that the different parts of the image offer different information. Could it be, for instance, or do you have any insight about? Could you have, for example, for your last work, to make it specific? I will make it specific and then more generic. Could you have different operations for different patches?
Different operations for different patches?
Yes. Some patches need more as opposed to others. It's when you are upsampling a wall. Not sample when you are upsampling my little server. Maybe you need more.
I think this is quite interesting. But I mean, you would need to know where you are in the
semantic.
In the semantic, to see in the neighborhood of yourself, to see like if you're in a flat space or very in a space with a very sharp contrast. But I think this may be related with the local attention idea that I suggested, is that you do not need to see the whole feature map, and instead, in fact, maybe I can show you a slide. So this is the attention map that we obtained in Japan, with the white dots. I don't know if you see. Yeah, the white dot here is the selected query, and it's a selected query, and the rest and the map is the attended keys. So in fact, you attend the keys that are in fact in the neighborhood of yourself.
Okay.
And so, I'm not sure this would bring. I would not expect significant gains modifying this, like allowing to see in a much larger neighborhood than just around you. This is a super strong inductive bias, and it seems to be sufficient to do this task.
Okay, thank you. That answers my question. But I will conclude by saying I really like the pro and con things that you have at everything, and the challenges. It's very clear and it's very well structured, and I like the name Safar.
Thank you very much.
That's fun.
This is the thing I'm the most proud of.
Okay. Thank you very much, Vicky. So we are going now to ask your supervisor, like to say a word. So perhaps the question will be light or even no question.
Super.
Comments, positive comments, so you can try to relax a little bit more. All right. So Jean-Emmanuel first, perhaps.
Yes, so thank you, Mr. President. So, yes, no question. Just I would like to echo positive feedback concerning presentation and your manuscript. And thank you very much for your good work. Interest, we appreciate your innovative approach. And this approach is aligned with topic area of interest concerning semantic segmentation, and its aligned and how we can improve perception in the context of situational awareness. So we appreciate your different approach, and we appreciate your disponibility, your curiosity, your investment of your work, and we like to when you share with us the evolution of your work, and it was a good pleasure to accompany you during this.
Thank you very much.
It was a real pleasure, and we see a good evolution during these 3 years about your autonomy and about how you have a problem or issue and how you could tackle this problem, and it was a real evolution. Thank you very much.
Thank you, man.
And thank you very much, Nicolas, to supervise you to obtain these those results.
Okay, thank you very much, Jean-Emmanuel. So now, Nicolas, I think this is your time. Okay, please go ahead. Yeah.
Okay, thank you, Mr. President. Can you hear me well on the room?
Yes, very well.
Great. Okay, so first of all, I would like to thank you all guys, for all the jury members for your involvement in this jury defense and the precious feedback that you gave us. So thank you for all this in this very busy period at the end of the year. And Paul, congratulations, of course, for the presentation that you gave us today. That was excellent. So despite the technical issues that we encounter, that by the end of the day you had very long and rich exchanges with the jury member. So congrats for all that. I would like to congratulate you more generally for the excellent work that you have been doing in the last 3 years. So as Jean-Emmanuel, so of course I also would like to thank Jean-Emmanuel and Thales for the collaboration that we had during this industrial PhD. And as Jean-Emmanuel, I have no technical questions since we have been working closely together during these years, but just I would like to take the opportunity to give some comments on your PhD journey and works. So in my opinion, one key strength of your scientific approach and personality is that you really tackle, so I think it's obvious when you look at your presentation and chapter, you tackle your problem really from an engineering perspective, but really in the positive sense, meaning that you were really trying to find the best pipeline for a given problem, and then you have been very successful and effective for that. And I think it's also clearly obvious and visible on the contribution that you had for each method. You were able to bring really to push state-of-the-art result very significantly. So especially, for example, in diffcut, so the approach has been used later on by other students in the team for unsupervised clustering. So congrats for all that. And of course, beyond this empirical performance and success that you had, you have also been gradually improving in providing methodological contribution, and as you have been successful in publishing your method in top tier venues. And you have been also gradually improving in writing paper and also independently drawing relevant research ideas. And especially that, so now at the end of your PhD, you have a really clear and personal idea of where you want to go. And for example, it was really clear during the discussion, for example, your personal idea on what are the next steps to combine self-supervised learning, representation learning method, and generative models. And I think these plans will be very promising. So yes, this concludes my comments. I wish you the best for the future of your career, and I am convinced that you are in the right track to become an excellent researcher. So
Thank you very much.
Thank you, Nico. Okay, so it's my pleasure also to conclude this session. I would like to also congratulate you, I mean, like, for your fantastic presentation of today. I mean, like, I really appreciate many things, and as Stefan say, it was very, I mean, like, complementing, I mean, like, the manuscript, and able to put everything in 45 minutes. It was not easy to do it, so I was not involved, I mean, in the first project, but as I was participating with the second and the third one. I really, I mean, I just want to complete perhaps one thing Nicolas mentioned. I mean, like, is that, I mean, like, this first project was very, I mean, like, difficult. I mean, like, to go at the end at that time, it was not clear if it was good or bad idea to use Atlas.
Yeah.
You really, I mean, I try many things, and so you have been very, I mean, like, clever to jump on other things after, and trying to just to take the benefit of your understanding about the video and editing, the diffusion models, and so on, to be able to jump to another thing. And it was not easy, and you perfectly done that. And after you were much more successful, I mean, like, for the third and the second and the third project. And so it's always, I mean, like, very how to say, I mean, like, cool and make us happy. I mean, like, when it works like that, and of course, and so at the end of the day, you have done a wonderful thesis, and so really, I mean, like, I'm very happy about that for you, and also to see that you were, I mean, like, able to collaborate with other PhD student, Mustafa for the second project, Loic and other for the third one, and so it's also a great thing to see that you are now, I mean, like, in the lab. I mean, like, I'm a key person to work with. Okay, and so thank you very much for that also. Right?
Thank you very much.
Okay, so this is ending, I mean, the Q&A session. Now we have to deliberate the jury. So the best thing is that. Except if there is a doctor that who wants to ask something, I mean, like, except the family, please. No, yeah, Mustafa, you are not yet doctor. Okay, all right. I don't know. It's okay. All right. Okay. So yes, perhaps on va rester ici, nous.
On va rester ici, ouais.
Okay. N'allez pas trop loin. We stay in the room.
Maybe would you mind stop sharing your screen so we
Yeah.
can see them properly?
It's good.
Also, I see that it is stream live on YouTube, so maybe if you can stop streaming it.
Maybe move the window here. Maybe stop sharing the screen. Window.
Exactly. Do you know how to start the library?
Go and you have this kind of YouTube.
Yeah.
There? Okay. Arrête.